Uroš, please tell us about colloidal structures in pneumatic lattice.
Okay, thank you very much. So, good afternoon also from my side. So, I will continue the story from yesterday when we were focusing actually on single particles in the pneumatic liquid crystal. And today we will be dealing with many particles which can be assembled into interesting structures. So, you can see already here few very colorful images, photographs, and here in the background you can see how the pneumatic film, so thin film of pneumatic liquid crystal on glycerol is organized, and you can see that there are a lot of defects, a lot of changes in time and space, and this is the reason why you can see such unhomogeneous motives actually. On the other hand, if you order particles like in this cases in the middle, you can see that these colors also get in much nicer shape and they are arranged more periodically. So following the outline, I will mostly talk about directed assembly of spherical colloidal particles by using laser tweezers. And these structures were assembled mostly before Ivan was starting using his wonderful equipment and two-photon lithography and so on. But still, with spheres, you can still produce many interesting structures, and you will see how to do that. What is to emphasize is the role of defects. So the localized singularities which we saw that appear close to the particle surface, and which are responsible for elastic forces which then bind these particles together. So first I will start with describing one-dimensional and two-dimensional dipolar structures, and then on the other hand we will go on with one-dimensional and as well two-dimensional quadrupolar structures. We will also take a look on the combination if you mix dipolar and quadrupolar particles together, and we will also see that it's possible to realize three-dimensional dipolar lattices. Before conclusion, I will actually talk about non-singular binding in twisted pneumatics, where you can produce defects which are different from those which we met yesterday, and they still can be used to bind such particles very tightly. Here is just one example. So what is the motivation to organize such colloidal particles into more periodic or ordered structures? So one of the things is that people want to produce colloidal crystals which tend to be used for photonic applications, and they can do this in many different ways. So here are examples of just the position of material on some flat surface. It can be done by photopolymerization or by micromanipulation with different kinds of lithography. So this is one option, and you can see some examples where such different arrangements of particles can control the reflectance of light. For example, you can also use particles which are anisotropic in their shape, and here is the principle where you have a contact line, so slowly evaporating liquid, which then tends to align with particles also in referred to direction. Or more recently, people are also using so-called self-propelled particles, where you can activate the motion of these particles by shining the light, so which is close to UV, and by this you can also gather such particles together to form such nice clusters. These ideas are also related somehow in one way, so how to control the flow of light in such structures. This is just like one of ideas. And so this idea of photonic crystals actually started by the seminal paper of Elia Blomovich almost 30 years ago, actually. And on the other hand, if you combine particles which have different dielectric properties, you can produce also kind of metamaterials, which are also popular research topic in recent years, which allow you to, for example, to get or to obtain many unusual physical phenomena like negative index of refraction or producing invisibility at some frequency range. So this is also why it's important to find techniques how to organize small particles which are comparable to the wavelength of light into ordered periodic structures. Yeah, here you can see some further examples where these structures are organized in nematic liquid crystal. I will talk about such things in the following. And it's important that you can reconfigure when you assemble the structure, that it's possible also to reconfigure it or to tune at least the separation between the particles. And here you can see some examples of such colloidal crystals and some gathering of colloidal particles at the interface between the nematic and air. And there you can see another lattice with some vacancies in the middle, so it's possible also to get the lattices which are not fully covered just with particles. On the other hand, you can produce structures which are connected with land effects. About this I will be talking tomorrow and in the last lecture, next Friday, and you will hear a lot about this in Ivan's next lecture. So about this kind of structures here. And there is just one example of tiling with pentagons. So you can also make quasi-crystalline templates or motifs out of colloidal particles in nematic liquid crystal. So those structures were mostly confined to two dimensions, so they were two-dimensional, but there are also several examples of three-dimensional colloidal structures, and they form somehow most naturally in blue phases, where there is a generated, or spontaneously, let's say, generated array of disclination lines, which can trap small non-particles at their crossings. One example you can see here. You can also produce such an inverted matrices, and then the defect lines will start to tangle around such opal-like structures. You can also increase the concentration of colloidal particles and get kind of self-quenched gels, which have high shear ratios and respond or behave very differently at different temperatures. You can also assemble the particles inside spherical geometries, for example, inside liquid crystal droplets or liquid crystal shells. And you can control the behavior or the position of defects actually by changing the geometry of the particles. So if you produce colloids of that shape, for example, or if you rearrange them in different planes. So if you produce kind of three-dimensional structures, in this case, I will be discussing some of these things in the following. So just to remind you, we are talking about now colloidal dispersions, so dispersions of small colloidal particles in nematic fluids. I will be concentrating on spherical particles, and what is important is that we induce the surface anchoring, so the orientation, preferred orientation of liquid crystal molecules on the particle's surface. In our case, it will be mostly homotropic, so perpendicular orientation of molecules everywhere around, and we will be changing the orientation of molecules on top and bottom glass plates, which confine these particles in space. And here you can see just two examples of this, our elementary building blocks we will be using. So on one side you have dipole structure with small defect ring next to the particle, and on the other hand you have a Saturn ring configuration where the defect is encircling the microsphere. So defects are important, and they are produced because we insert the particles into a homogeneously aligned liquid crystal. So that's why they have to appear, because you have to conserve the topological charge, and because the particles disturb the liquid crystal, the defects start to appear next to the particles. And these defects, as we have discussed already yesterday, have different topological charge. They look differently, so they can be radial or they can be hyperbolic cross-section. And on the other hand, we'll be mostly dealing with explanation loops, not today, but in the next talk, which have also hyperbolic cross-section. If we take a look back to the history, so when the colloidal ordering in pneumatics fluids started to be studied, okay, we mentioned last time the seminal paper of Polan and co-workers in Science in 1997, and then the field somehow began. This field started to be researched more intensively. And what people were doing is, here is one example, they were just studying the mixing of two fluids, so of silicon oil in pneumatic liquid crystal, where such spherical droplets start to appear at some temperature, and they of course induced topological defects next to its surface and started to organize in such a parallel actually dipolar chains. On the other hand, people studied also the droplets of glycerol at the interface of pneumatic and air, and in this case the defects appeared below these spherical droplets. And because the location of defects was different, also the positioning, so the minimization of their energy led to differently organized structures, typically to some kind of hexagonal crystalline structures at the interface. Shortly after this, researchers were started to using laser tweezers to manipulate individual particles. And this helped a lot to study interparticle interactions. So you could start to study how anisotropic in nature are these interactions between separate particles, and then this also opened the possibility to control the ordering in a more controlled way. So not just like the mixing from the bulk, or just looking at some droplets which starts to appear and gather together, but really to control and position individual particles very finely. Okay, before there were also some studies of chains and such an isotropic clusters which were formed spontaneously in the pneumatic matrix. And here you can see also some examples where you have tangential anchoring of the spheres, and they again tend to align into linear chains. So if we take a look now on the interactions which can happen between two colloidal particles which are immersed in the pneumatic fluid, we can again use the analogy with electric charges. And in this case, we can approximate the energy by different contributions. So in the first case, we have like column-like component or potential, which we saw when the particles were attracted toward the focus laser light, so the optical tweezers, we will see that if we have a combination sort of two dipolar particles, for example, you get a force which is scaled 1 over r to 4, but if you calculate the potential, you have one exponent lower here, and if you mix, for example, dipolar and quadrupolar particles, you get one order higher exponent below, and for quadrupolar component, you get 1 over r to 5. This combination. So these interactions actually follow the power law, and in addition to this, you also have some screening of this interaction if the confinement is strong. So if you suppress or press the particles quite tightly between the boundary substrates.
Excuse me,
Yes.
Does the electrostatic analogy still work with unequal Frank constants?
With unequal Frank constants.
Yeah.
So if you're not using a single constant approximation,
Right.
I'm not sure about this, but I think not really. But so in this electrostatic approximation, you're looking at the far field, actually distribution of the directed field around the particles. So this is kind of approximate, let's say, approach just to get out somehow the behavior which responds to some of these power laws, so that you can distinguish different anisotropic interactions between different particles. But it's not meant to be such a strong analogy that you could incorporate also some other details. Okay, so we take a look first at this dipolar colloids, so which have a point defect next to the surface plate here, and you can see two examples how they get ordered. So in the first case, you see that the dipole, if we look at this arrow, so which is pointing from this plus defect which is inside the particles towards the hyperbolic defect which is negative next to the particle, you can see that they tend to align in parallel. So they are forming linear chains. If they approach, so if we find the close distance, they approach to each other and make such a pair. On the other hand, if you have two anti-parallelly oriented dipoles, they will also attract at some angle. So they don't go together exactly in the same, the shortest distance as in the previous case, but they make some longer paths and tend to align anti-parallel. And you can see that these forces or this interaction potential is very strong. So you can see that this interaction is measured in the units of several thousands of kT, which is much stronger than you can achieve in water-based colloids. And this is also the reason that the elasticity of the liquid crystal, which is in between these dispersed particles, mediates this long-range ordering, actually. So this is the first case which you get if you're studying dipolar particles. If you increase the density of the particles, you can get larger structures, of course. So first you can study the chains, which tend to be oriented at different directions, which can be oriented to different directions, but here we just have all in parallel, and they repel each other. So if we look at these two dipoles, if they are parallel, they don't want to stay in this position. They will repel and go apart. So if you turn around the position of the defect from upside to down, you get, instead of repulsive interaction, an attractive interaction. So like we saw just before, if you have anti-parallel arrangement of dipoles, they get strongly attracted. And this is very useful actually, because you can make chains of dipolar particles which are oriented in the opposite directions. So in one chain, defects are pointing up, and in the other one, they are oriented in the opposite direction. So you get attraction between these two chains, and you have attraction between the neighboring particles along the chain as well. And this is then the principle how to arrange larger structures. So you can combine different chains together, and you see that there is some interesting effect related to the odd and the even number of these chains. So the reason is that you produce some elastic torque which has to be relaxed if you have an even number of chains. But if you have the odd number, there is no elastic torque, and the structure is oriented actually in this normal, along the director in this direction. So if you increase the number of these chains, of course, this effect disappears, slowly disappears. So this was somehow the recipe how to organize larger dipolar crystal lattices. And you can see some examples here. If you gather together, let's say, about 200 or 100 particles, you can produce a very nice lattice of dipoles. And they resemble, so their arrangement somehow resembles, it's like anti-ferroelectric lattice, let's say. So you have anti-parallel arrangements of dipolar chains in this case, and the structure is very stable, and it also has very nice properties if you look at them. This structure under polarized light. So this color somehow reflects the radiation of molecules around the spheres. Yeah, so when we have assembled this structure somehow, then the next step was somehow to try to use them for some interesting application, or at least to show some principles which can be useful. And the first thing is that such structure responds to external electric fields. So if you apply the electric field in the perpendicular direction to the structure, you can change the distance between the colloidal particles. So the structure can shrink, and because of course the liquid crystal molecules tends to orient in the direction of the electric field. And you can then study the propagation of light or the diffraction of light which is shining through such a lattice. And this way you can produce kind of tunable diffraction rating, because you can change and modulate the intensity and the frequency of the external electric field. So one step forward was done recently where this structures of dipolar structures were stabilized by polymerizing the liquid crystal matrices. So if you use some material which can be polymerized by a higher temperature, you can, after you sample such a structure, so it's still pneumatic fluid, but you add some chemicals, you get cross-links, which then lock the structure. You can then actually take this structure, so the polymerized structure, out of your sample and transport it somewhere else, for example, or you can build larger arrays and then again use it as a diffraction gratings. Of course, in this case, you can also tune the distance between dispersed particles, and if you're using external electric field which shrinks your structure or expands it, depending on the dielectric constant of the material, you can can then also polymerize quite quickly under applied electric field, for example, if you want, so you can get this lattice parameters of different kinds, also in polymerized, which is more solid than structures. Okay, now we can move on to the quadrupolar kind of pair interaction. So in this case, you study how two particles with encircled Saturn rings would interact and what would be the most energetically most suitable or favorable position for such a pair. So here you can see that they tend to align at some angle, so, which is about 20 degrees if we look at from this direction. Or there's written 79 degrees, and this is somehow the equilibrium position if you try to push together or bring two such particles to the close distance. And the binding energy in this case is lower than previously. It's about 1000 kT, which is still quite strong for several micrometer big particles. And you can observe also that the symmetry around the directional field around the particles is different than before. And in this case, you actually have 4 symmetric positions where you can bring another particle to the already assembled pair. So if you, again, increase the number of dispersed colloidal particles, you will observe the formation of quadrupolar chains. So they can somehow extend in 2 different ways. So you can build or assemble straight chains, which are extending along an angle which is typical for a quadrupolar pair, so you're just attaching more and more particles, or you can make such a kinked chain, so where the position the particles go up and down. And if you increase the concentration of these particles, you can see that you get an area where these particles are assembled into kind of rhomboidal clusters. So you don't have only chains, but you get something which is 2-dimensional and which is quite nicely ordered. And we studied also then the interaction energy, so if the particles are brought also along the lateral direction to this quadrupolar chain, and you can see that in this case you also get a little bit, again, weaker attractive potential, but still strong enough that these clusters or larger clusters can be assembled and remain stable actually for a relatively long time. So the next step is of course to organize larger and larger structures out of this interaction, and here is an example of quadrupolar crystal lattice where you can see that, at least in simulation, that these colloidal particles which encircle the Saturn rings form very nice hexagonal-like lattice which binds all these particles together. And okay, this structure is maybe a little bit less stable because the binding energy and potential is not so strong in the previous case of bipolar crystalline lattice. And after a few weeks or some months, you can see that this thing gets slowly destroyed or disintegrated close to the edges. Okay, maybe it's time to give a question for you. So now I would ask you why or how do we see these beautiful colors under the microscope? What is the reason? So we have several options actually to choose, and I should start now this. I think that the answer is not, or the question is not so difficult. So. one we'll be talking about on Friday, I think, and also like particles cause very similar effects as spheres. So we will take a look now what we got for the answers. Yes, so the majority, of course, of the answers is the right, so the last one. It's true that we have to use crossed polarizers, but we also have to insert the retardation plate to get such nice colors, because then we get this shift in the wavelength of light, and we can distinguish two perpendicular orientations which appear with the same color, just only crossed polarizers, but here we get two different colors. So on one side yellow, and on the other side blue one. Yeah.
I'm sorry, I missed that. What would you see if you did not use a retardation plate?
If you don't use the retardation plates, you see mostly dark, so wherever the orientation of the molecules is parallel or perpendicular to one of the polarizers, you see black, and in between you see just bright. So you cannot distinguish actually the colors, but here you see the orientation which goes from this direction into this as one color, and on the other hand, the other orientation which is perpendicular to this as the other color. So you have two different speeds. I mean, the light goes through the polarizer and through the retardation plate at different speeds. If it goes, of course, parallel to this plate, or if it goes perpendicular to this birefringent material. So you can distinguish then how the molecules are oriented around the particles. Because if you would not use the retardation plate, they could be also assembled like that. So, like tangential ordering, because you would also have then some parallel orientation to the polarizers. But in this case, it's clear that they are homotropic, so that they are oriented perpendicular sphere. You get two different forms. So you can use then this Michel-Levy chart with birefringence, and you can read out actually the orientation of the molecules according to the colors which appear under the microscope. Okay. Yeah, I want to show you now maybe just a few movies. So how does it look like in real time if you want to sample such things? So in the first case we have a dipolar chain and one dipolar particles which will be manipulated by the laser tweezer. So you can grab it and pull it around. You can change. So okay, now the dipoles are oriented in parallel, and you can clearly see this repulsion. So the particle does not want to be close to the chain because the defects are oriented in the same direction. But if you change the position of the defect, so turning around this dipole, you also change the interaction from repulsive to attractive. You can see that this particle is now strongly attracted to the chain. So if you have, for example, two parallel chains, they also start to interact, and they're moving and forming about the structure. Similar happens also with quadrupolar particles. Here we don't have such a strong interaction, but the particle approaches more slowly towards the structure. But if you use, so this is just like spontaneous assembly, so you just have to bring them close enough to each other. But if you're using tweezers, you can pull them more quickly and more tightly and tag them actually at the edge of this already formed crystal. So you can take the laser beam of not very high intensity and also correct a little bit the positioning of the particles in all the formed structures. Okay, so another step what you can do is that you combine distinct quadrupolar particles. So you're not having only the Saturn rings, but you can have also these bouillons. So if you insert the particles which have tangential anchoring on each surface and mix them with the particles which have homotropic anchoring on each surface. And in this case, you get two types of quadrupolar particles, and of course they behave again differently than we have seen before. So in this case, you have two perpendicular directions of attractions and two perpendicular directions of repulsion. And you can see that by using such kind of particles, you can form actually also interesting colloidal lattices. Here is just one example of that, of this kind of interaction where each bouillon particle actually with tangential anchoring on the surface is surrounded by four other particles and vice versa. So you get a square-like colloidal lattice in this way. Before we had just like hexagonal or hexagonal lattices. So if you combine this, you can change the symmetry of the forming crystals. There was another study where the interparticle interaction, mostly between just two particles, was recently studied in polysteric, in highly twisted pneumatic, and there it was found that you get different metastable states and different minima in this attractive potential, and you can see that if you have just a uniform pneumatic, you have straight attraction between the particles, but if you induce the chirality, you can get different metastable positions between reaching and the final configurations when these particles really come close to each other and typically also get entangled because they have kind of entangled defect line around it. And here you can see that this chirality actually is screening somehow the interactive potential and does not allow such a direct attraction between the particles. So you have kind of oscillatory nature in this interaction. So particles can approach at some distance, then they stop, stay there for quite some time, like here, and then when they find the right position, they again start to approach and finally form some structure. So there are more potential barriers actually in between than previously. So another option which you can do is that you combine dipolar and quadrupolar particles. So you can reach this in some intermediate region with selecting such a thickness of the cell where you have a population of both, so a mixture of dipoles and quadrupoles in some region, so which is related mostly to the particle size. It should not be too much space above and below the particles and not too little, because if you squeeze them very tightly they will form quadrupoles, and on the other hand if they have too much space they transform to dipoles. And in this intermediate regime you again get some attractive interactions, and you get at least these two options of metastable structure. So dipolar particle likes to bind to the quadrupolar mostly in this configuration, but they stay together also in the perpendicular direction. Not so tightly bind, but still. And then it was also shown that if you study the interparticle interaction more precisely by positioning two particles at close separation, you can see from which directions you get the attraction and where you get the repulsion. And by measuring the trajectories and then again by calculating the interaction potential and force, which is responsible for this interaction, you find out that it is proportional to r to the 5th degree in the exponent, which is then typical. So in between what we have expected or calculated for dipoles and on the other hand for the quadrupoles. So this was just confirmation that this is also possible and experimentally realizable. Of course, with such a configurations, you can again form a big number of different metastable or also relatively stable colloidal lattices. And what is the difference from before when you're using just one kind of particles is that you can get also structures with some vacancies, so it's not necessary that particles are fully filled inside this crystalline structure, which can be also useful, because if you have a material, liquid crystalline material, which have one kind of refractive index or dielectric constant, you can combine them different kinds of particles or particles with different dielectric properties, for example, in one lattice or in one configuration. And again, you can see here that actually the anisotropy of these interactions is strongly depends on the type of the defect which you have. So if you combine dipoles and quadrupoles, you have different distribution of attractive and repulsive interaction around a single particle than if you are using just the same kind of the particles. And in this case, you get also so much stronger deformation of these defect rings, at least in simulation. This can be much better seen than otherwise if you're using just one type of the particles. Okay, now I'll proceed to the next topic, which is related again more with dipolar particles. So in all previous cases, actually, the particles were confined in planar cells. This means that the orientation of the substrates was more or less so in parallel directions. And in this case, this orientation of the substrate is changed from planar to homeotropic, so to perpendicular. Now we have the magnetic field is directed actually towards the wall. And in this case, also the position of the defect, which was before just in the plane, is changed so towards the wall. So the defect is now will appear below or above the spherical particle. And you can see this quite nicely already here, because you can see that you get nicely ordered structures here of dipolar particles, which are not all in the same focus, so are not in the same height. So some of them are lower, some of them are higher. And this is somehow the recipe actually to achieve also the three-dimensional assembly or three-dimensional lattices of dipolar chains. So in this case you can see how the position of defect, so if it's above or if it's below the particles, looks differently under cross polarizers and even without polarizers. And then you can use in a similar way, like we did actually for two-dimensional crystals, to alternate the particles with upright and downward position of topological defect to form such a zigzag checkerboard patterns in lateral directions. So you get such a nicely ordered structures there. And if you take a look at the unit cell of such a structure, you can of course see very quickly that it's tetragonal, that it has tetragonal shape, where all particles in the corners are oriented in one way, and the particle which is seated in the middle has to be oriented in the opposite way, just to minimize the elastic distortion. Again, you can use the laser tweezers to bring separate or individual particles together, first to form chains now in this perpendicular direction, so you position them closely one to another. Of course, in this case you need more space, so you're working in thicker cells. And we try to assemble actually first the vertical chains, which can be then again put together to form larger clusters of blocks, colloidal blocks. You cannot do now one by one actually, because you will destroy, or so this is not the good way, just like before, to bring, but you have to organize them in chains first. And then you have to bring together 2 or 4 chains, which form such a stable cluster, and when you have this, you can arrange a larger number of such clusters together to get a crystalline lattice, at least, at some size. So in this case, you have 6 by 6 by 3 layers of dipolar particles. And you can scan this also by confocal microscope, and you can observe the arrangement in different layers. And you can see some relation also to two-dimensional colloidal structure. So there is no simple stacking of the chains like before, just in parallel, but you can see this arrangement along the diagonal of such three-dimensional structure. Okay, so before concluding this lecture, I will like to say a few words about another type of defect configuration, which is not singular, but is escaped kind of defect. And okay, here we can see the example that all the point defects likely transform to small loops, or declination rings. And if we have pneumatic colloids, we can bring two dipolar particles closely together. Okay, they don't like this position. We have seen that they made some way around to get attracted. But if you force them to do this, you can form another kind of defect, which was named bubblegum defect. And it was actually very rarely observed in planar pneumatic cells. So it was observed already in 1997, so when this modern age of pneumatic colloidal science started. And it was studied, briefly actually, how it behaves, how it interacts. And it was shown that you have string-like force dependence on separation between the particles. And it was also somehow predicted that out of this you can possibly get chiral colloidal dimers in non-chiral medium, and that you can achieve kind of superelasticity due to the absence of this topological defect. And we will see that this can be better, even much better studied or distinguished in twisted pneumatic cell. So if you break this symmetry, if you make a twist, so from below to the top, molecules have to turn from one side to the other, either to the left or to the right. You get a twisted environment, and this shifts the position of the defect as well. So in the middle you have some average orientation, let's say in this direction, and the position of defect, which sits in the middle next to the particle, also goes there. But what is different is that in this case you don't get the formation of dipolar chains, but you get formation of anti-parallelly oriented, mostly this elastic dipoles. So there is no preference where this defect will sit. It can be on this side or on this side. So it happens just randomly. But when particles come together, they start to interact. And of course, these defects want to avoid each other. And what they do, so you can see in this sequence of images, so when they are brought closely together, they start to interact, defects want to avoid each other, and they transform into different structure. So it is different just by looking at it, and actually you can find that there are two different configurations which appear differently under the cross polarizer. Actually, if you just look at them or take an image with color camera. So the structure which is in between them should be different as well. And somehow what is the reason or what is the difference in this case? So as we have seen, they are actually now sharing a loop of topological charge -2, because they are made of 2 - 1 defects, actually. And in this case, this is just the case from the planar cell, where you can hardly get this situation, but it's possible. And you can discriminate this much better in this nematic cell where the symmetry is broken. So what you get is that in this case, so the orientation here at the edge of this defect can escape in two perpendicular directions. So in one direction up and in the other direction down. And this can happen in two different ways, actually. So this means that according to the twist which is around the particles, so you are in, let's say, right twisted or left twisted nematic domain, where the preferential direction is chosen in one direction, and the defect likes to escape in the opposite direction. So to compensate somehow this twist which is exerted on the system from the environment. And you can then distinguish, of course, if you use laser light, if you use manipulation, so strong optical trap, you can reverse this direction of escape. So you can form the combination where the defect goes in the same direction as the twist is imposed on the particle. And you can see then this also nicely, so how this defect structure is still defect structure, but it's not singular one, appears if you use like some display band parameters and how the twist is changing close to the core of this deformed region. Okay, this is just what I was telling you. So this director escape mechanism you can see more nicely here in this case. So if you have such a hyperbolic cross section, this configuration is energetically highly unstable or unwanted. And to release this distortion, the molecules tend to turn in one direction towards the wall and in the other direction out of the wall. So in this, because you have two perpendicular directions, this can happen in one direction inside or outside, but these two cases are different. So you have like a mirror symmetry in between. And if you say that this one scenario happens on one side and goes then around, so the loop, so the defects which are there wants to form a closed loop, you get escape in one direction or in the opposite direction. And you have two mirror actually configurations which are typically much different in their energy, because the twist of the environment which is around is favorable for the opposite handedness of this escape. And these are again a little bit analogous to the skyrmions and chiral, these states in chiral ferromagnetic materials, where they also observed skyrmion lattices, so where you have this tilting of magnetization out of the plane, and this is also kind of a hot research field in recent years. So where something very similar actually is happening in much smaller scale with different material. Okay, so if we try to pull apart these two particles, or just pushing them apart with a laser beam, you can again see that they interact with string-like potential, so the force is practically independent of the separation between the particles, and you can use them to assemble larger structures again. So if you position them in such a pair bounded with this escape defect and study how they will position next to each other, you can see that they are attracted from practically all sides, or at least these four sides, and they form again a square lattice, which is not very usual for spherical particles. So this fourfold symmetry, which we have here. And now we have an opportunity actually to assemble dimers, colloidal dimers of one kind of chirality, let's say, or one kind of escape, or the other one, just using the same kind of particles, or you can also mix them together and do some alternating grids. So where also the light which comes through these defects is differently reflected or also transmitted. Okay, this is just to show that also the numerical modeling fits well together with experiments. And I would like to conclude now with some further reading, because so the nematic colloidal dispersions of microscale and nanoscale particles are still quite active research area, and you can see just a few recent review papers. If you are interested to read something more about these systems, you can also find a bunch of references in there, and their relations on how also to, on one side to topology and on the other side to photonic applications. And just to show me that people are still working, of course, in this field, so you can see that in the last 20 years there are almost 600 papers published. If you just type in, there are, I think, more. If you just type in this phrase of nematic colloids to the Web of Science, which means approximately in recent years, approximately one paper a week, and that also the number of citations is growing year after year. Okay, in the end I would like actually to acknowledge to my co-workers. So again, above is the group of Professor Igor Mušević, so co-worker Uroš Tkalec, and two co-workers Andrei Nič and Juliana Lista from Ukraine, from Kiev, who are frequently guests at the Jožef Stefan Institute. And below you can see theoreticians, so Professor Žuma, Dr. Miha Ravnik, and Simon Chopar, and also Nathan Osterman, who's experimental physicist, but he was responsible also for this optical figures setup and also for some measurements. So I would like to thank you also for your attention.
Do we have questions? If not, I would like to remind you that tomorrow we have a poster session. And so this means you should bring your posters you want to present.